This evening. I'm sorry for all the technical difficulties. Dr. Mark Giampapa.
Well, thank you very much, and again, I'm sorry for all the delay. Modern technology is a blessing and a curse. Tonight, some information, especially from the sun, and the correlations of magnetic field strength and these spectral line emissions. And here is some early work that shows a spectral heliogram on the left, and on the right are magnetic fields, early magnetic field strength measurements on the sun versus the brightness in those emission lines, that in these bright regions that you see in the calcium 2 spectral heliogram. They measure field strength, so really magnetic flux, and you can see that there's an approximately linear relationship. Here's in this diagram. With increasing emission, you get increasing field strength. With considerable scatter in the weaker field strengths and lower emission. But I think in the new era of astronomy, in the next slide, and this kind of work is going to advance considerably, and we'll be able to significantly extend these early results with high accuracy magnetic field strength measurements. And like you see here is a model of the new telescope we're building on Haleakala on Maui. It's a 4-meter solar telescope called the Daniel K. Inouye Solar Telescope, or DKI Solar Telescope. And with that kind of aperture, you will be able to look at the sun at very high spatial resolution, at high flux levels, and be able to attain very high sensitivities. And I marked in the diagram on the left that in the infrared region, especially from about roughly 3.5 to 4.2 microns, there's an array of spectral lines available that extend from the photosphere through the chromosphere and into the corona of the sun, that we can get practically simultaneously to allow us to map the magnetic fields and the associated emissions in the sun. So I'm personally particularly excited about that. And the infrared is very nice because a little equation below describes how spectral lines are split in the presence of magnetic fields. And as you see, it goes as lambda squared, and it's proportional to the field strength B. And so as we go to longer wavelengths, the splitting increases. So that makes it easier to measure field strength, especially at low magnetic field strength, at high sensitivity. Next slide, please. And so one key discovery of 20th century astrophysics was that the sun was a variable star, and we knew that in its magnetic field related emissions, like you can see in this diagram how in this case it could vary with rotation, although you could also think of it as a cycle time scale as well, multi-year cycle time scale as well as a multi-day time scale. If you advance again, there's a variation in the total solar irradiance that's associated with that. And this is the irradiance from a number of satellite experiments versus years. And the sun over a cycle time scale showed about a 0.1% variation in its bolometric irradiance. And on shorter time scales, and you can see a bunch of little dips, especially obvious in the blue panel, the blue curve above, and those are due to the disk passages of sunspots, so those are about 0.1 to 0.3%, depending upon what phase of the solar cycle we're in. And again, during solar minimum. And so the sun is actually a little bit brighter at solar maxima and a little bit fainter at solar minimum. So given that result, next slide please, it was natural to ask, well, do stars, sun-like stars, show the same behavior? And so a program of very high precision photometry was undertaken by some of our colleagues at Lowell Observatory in Flagstaff, Arizona, on Mars Hill. This is a picture of a 0.5 meter reflector that was at that time dedicated to this project, which was carried out in the 80s and 90s. And the diagram on the left shows the amplitude of brightness changes in these stars versus a measure of their strength in those calcium emission lines. That is a measure of their chromospheric emission strength. So brightness increases up to the left, and the chromospheric emission strength decreases to the right. And you can see the sun is plotted there with a circle dot, and it looks very quiet compared to the rest of the stars. Most stars have higher, in this diagram, higher amplitudes of changes in their brightness. And then as you go to higher chromospheric emissions, you get even higher amplitudes. As you recall, I said the sun was through its whole wavelength region was up at about 0.1%. But here you see stars that are 10 times that and more. But of course, there's an observational bias there, and that those are the kinds of amplitudes that from the ground we're able to measure with this high precision differential photometry. Now, this kind of work, next slide please, has been extended in the new era of astronomy with particularly the Kepler spacecraft. And then below that is the WIN 2.5 meter telescope on Kitt Peak here near Tucson, Arizona, and it was used to look at Kepler field. So now we have this diagram you see that shows the range of photometric variation in millimegs versus, again, that same parameter indicating chromospheric emission strength. And if you click again, I put here approximately where the sun would lie on this diagram. So now with the Kepler spacecraft, it has very high photometric precisions that are unattainable from the ground. And so again, you see the general correlation of high amplitude photometric variation with increasing chromospheric emission strength that's associated with magnetic fields on these lake-type stars, although you see considerable scatter too. So a star that's at a particular chromospheric emission could have either low photometric variability or very high photometric variability. And the sun, in this case, is not exceptional in its quiescence. In fact, it almost appears to be at a boundary between the most quiescent stars and the most active stars. Now, if we go to the next slide, this is a little more sophisticated, but the idea is to convey that the rotation of stars is a key parameter in producing this kind of stellar activity. And here is a diagram on the right that shows a measure of X-ray emissions versus rotation period. So the rotation of the star is getting slower to the right, and the X-ray emission is increasing upward on the left. And you can see that stars have a sort of maximum X-ray emission, which comes from the hot corona of the star, and then it begins to decline as with slower and slower rotation rates. And the rotation of the star is apparently controlled by this little diagram on the left shows which attempts to show the effect of winds coupled to magnetic fields, and they carry away angular momentum from the star and break the star, and that is, break the rotation of the star. So in that sense, the magnetic fields in the sun and the star, the energy in those fields is very, very small compared to the total luminosity of the star. Nevertheless, they're dynamically important in the sense that they determine the rotational evolution of the star and modulate their luminous output. It's the source of small amplitude photometric variability, and the fields are also the source of rotational evolution in stars. Now, in the next slide, the rotational evolution may be complicated, potentially, by the existence of planets. And here we see a somewhat complex picture where a theorist has developed a model of the magnetic field lines coming out of an active M dwarf star. And the picture on the right is the depiction of an extrasolar planetary system around this M dwarf star. And you can see the planets in proximity are rotating through the coronal magnetic field region of the particular stellar model. And one hypothesis has been that a planet could, especially when it's close to the star, could block some of the winds that are coming from the star and slow down this rotational braking. And so, next slide, the question is, does that happen in reality? And the diagram on the left is a histogram of rotation for a sample of stars from the Kepler field. And this may indicate evidence of a possible effect, where they looked at in the blue, that's the distribution of rotation periods for stars that are not known to have planets in the Kepler field, while in sort of orange or brown, these are stars that are known to have planets. And the authors remark, my colleague Derek Bisashi and the students who wrote this paper remarked that the systems with planets seem to be shifted to a slightly faster rotation period. So the result is statistically significant at a marginal level. So while it's marginal, it's still nevertheless very tantalizing to explore the potential effects of planets on the rotational or angular momentum evolution of stars. And this may be potentially an indirect way to perhaps identify stars that may be candidate hosts for extrasolar planetary systems. But that would be only one of many other tools that are in use now or being developed. Next slide, please. Another approach that we're certainly exploiting in the new era of astronomy is to look at what we call more homogeneous ensembles of stars. Most of this work that I've described has been on field stars that are in the solar neighborhood. And they can have a whole variety of ages and chemical compositions and so forth. But I've been looking at a cluster, Messier 67, that has about the same age as the Sun and virtually the same metallicity. In fact, in the panel on the left, excuse me, in the panel on the left, we see a spectrum of a star in M67 that's in red, and in black, superimposed on it is the spectrum of the Sun at the same spectral resolution. And the bottom line are those two spectra subtracted. So you can see that the subtracted spectra are near zero, and showing that that the spectra of the sun and the spectra of these stars are virtually indistinguishable. So I've been using the WIND telescope with the multi-object Hydra spectrograph. It's a fiber-fed spectrograph where I can steer fibers to every individual star in the cluster I want to observe and obtain spectra, in this case of their calcium H and K lines, simultaneously. The diagram on the right shows some of my initial results, the histogram, where it shows the distribution of this index, the strength of the emission in calcium H and K, and the same value in the dotted line for the sun during the solar cycle. And you can see there's considerable overlap between the stars in F67 in their H and K strengths and that of the sun. So some are in excess of what we find even at solar maximum, and some are below even solar minimum. So one hypothesis is that the stars below solar minimum may be in a longer minimum themselves. And then the other question is, why are these stars that are even above solar maximum so active at this solar age cluster? And say, Claude, excuse me, I'm going to have to, I got to go get some water in my
That's fine. Go ahead. We'll stand by. And you can see in that histogram way off, there's two bumps, one way up at 350 and one up at 400, so anomalously high. I didn't notice those at first.
And they're, those are at M67, so they're all supposed to be the same age,
same age, same distance.
Well, Pedro's
Presumably these
Hi, Pedro.
G-type stars.
But yeah, that's remarkable agreement between the spectra.
Yeah, you almost can't see it.
Right. So a true sun analog there. 67 is an open cluster, I assume.
What is the diagram on the right again?
That is a histogram showing the
Yeah, the solid black lines are our histogram of the M67 stars, and the dotted line is the sun over the solar cycle.
as far as the that's the brightness index in the H and K line.
It's a K index.
And so that says that they're in solar. We're seeing a bunch of stars in different parts of their solar cycle.
Yes.
Yeah.
So by sampling enough, that shows a distribution as if they were across their entire cycle. So why are you getting those things way, way, way over on the right?
A few outliers.
those guys.
Yeah, some hyperactive stars over there. And you can see the new Discovery Channel telescope there on the right is a dead ringer for the WIN 3.5 meter. As I recall, the Discovery Channel I think is a 4 meter, so slightly higher aperture, but obviously the same engineering company was brought in to do their, at least their dome.
Yeah, okay, I'm back now. Sorry, the fountain is quite a ways down the hall.
No, we're still here.
Okay, great.
No worries.
Thanks. So we can go to the next slide. We'd like to expand these results in the future. And of course, in the new era of astronomy, we're building extremely large telescopes, such as shown here, the PMT and the Giant Magellan telescope. And a colleague of mine and I have formulated a proposal that we call the 1,000 parsec open cluster survey, which would be intended to use these very large telescopes to survey distant open clusters to gather more objects like solar-type stars at different ages. And the next slide, we have catalogs of clusters that are mostly complete about to 1.8 kiloparsecs, although their membership lists are poorly defined. But the astrometric mission Gaia will improve these membership lists considerably. We're really looking forward to those catalogs that will emerge. In the next slide, it shows clusters with ages greater than 30 million years, and two reasons that we need a large telescope is that when you go, of course, to greater distances, the objects are fainter, but the apparent size of the clusters on the stars, imagine, decreases as well. So here are size and degrees versus known clusters versus distance. And you can see that you rapidly get below 1 degree or get to a fraction of a degree pretty quickly with many of these clusters. The next slide, we talk about diffraction is limited imaging with, in this case, the TMT, the 30 meter telescope, and their infrared imaging spectrograph. So sunlight stars in, for example, this cluster M35 and FCA35 are at 14.5 to 16.5, but the bottom of the main sequence, as shown on the left, extends well below 20th magnitude. So we need a large telescope like TMT to not only see those faint stars on this cluster's main sequence, but also to have enough spatial resolution to resolve stellar companions and identify binary systems. And next slide. So with these kinds of large telescopes, we can, at faint magnitudes, do some relatively reasonable spectroscopy. And here's one simulated example, looking at, again, at the calcium 2H and K lines. We can look at all sorts of other spectral lines that can tell us about effective temperature and surface gravity and so forth. In the next slide, so in this new era of astronomy, we can explore what I call the solar-stellar extragalactic connection. Oh. Here we see the TMT with a picture, as you well know, the Andromeda Galaxy. And in the next slide, in that little square in the upper panel is an HST image. The TMT will enable near diffraction limited imaging as split spectroscopy over about 2 arc-minute field of view at near-infrared wavelengths. And at the distance of the Andromeda Galaxy, I can get to reasonable quality spectra in about 1 hour integration in dark moon. Now, in the panel below are clusters, star clusters identified in the Andromeda Galaxy. And there's on the right are blown up magnified images of these extragalactic star clusters in another galaxy. So this kind of program would, I think, be the first practically feasible attempt to identify and carry out a census of the properties of solar-type stars in an external spiral galaxy. And that would be, of course, that would have implications for studying the nature of solar-type star formation, including possible exoplanet system formation and sun-like stars outside our galaxy. So if you click again, I just give the observational parameters. Now, another problem in next slide, please, is another fundamental problem in the sun and sun-like stars is understanding the origin of magnetic fields, how they're generated, and how they lead to cycles like the sunspot cycle. And this is just a sort of little cartoon or diagram to try to illustrate where we think the magnetic fields are generated in stars. And in sun-like stars on the right, you think, they have a radiated core, and then they have a convective envelope, that the interface at the bottom of the convection zone, but outside the radiated core, is where fields are generated and amplified Then they eventually break out of that interface region and float to the surface. And then they appear perhaps as sunspots or those less strong, brighter regions. The other model is on the left, and that model suggests that all the fields are mainly generated in the convection zone. Now, certainly in M-dwarf stars that are fully convective, there's no longer that interface region between the radiative core and the convection zone. So one question is, well, would those stars, M-dwarf stars, still show cycles? And next slide, please. So here are some very preliminary results on just a few stars. And in about 5% of the targets observed, they saw some periods that were on the range of days to greater than 10 years, in addition to some long-term trends for some objects. And so we think that these may be manifestations of cycles in these cool dwarfs. It's still somewhat unclear, and the sample is very small. But next slide. In the new era of astronomy, I think the Large Synoptic Survey Telescope will add a lot more data to address this question. And the LSST is under construction now in the southern hemisphere in Cerro Patron in Chile. And its effective aperture is about, I think, about 6.7 meters. And it will survey the sky 2 to 3 times per week, and with these photometric precisions of 5 to 10 millimags. And from our preliminary results, that should be enough precision to identify cycle periods in M-dwarf stars, or perhaps not find them. And that would help us address, where and how magnetic fields in late-type stars are generated, with the wealth of data that will emerge from the LSST. I mean, and that's only one one problem. Now, next slide. Of course, in the new era of astronomy, we have new missions that are either operating now or soon will operate, and particularly looking for exoplanets. And in the course of looking for planets, especially transiting planets, it will gather information, as did the Kepler spacecraft, about stellar variability. Right now, Kepler is in flight, although its main mission is no longer in effect. It's still very useful in observing a variety of fields, mostly clustered around the ecliptic. But the next slide. The next major mission up is called TESS, the Transiting Exoplanet Survey Satellite. And it will survey the sky in 27-day sectors, and it will stare at selected fields for 27 days. Will mainly, therefore, find transiting planets that are close in short orbital periods, but it will gather some information about stellar variability, but its particular focus will be on finding terrestrial-like planets in the temperate zones of M-dwarf stars, which, because they're cool, the habitable zone is very close to the star, like typically 1/10 to 2/10 of an AU, which, as you know, is inside orbit of Mercury.
Excuse me, Mark.
Yeah.
Tess, will it come back to certain fields and repeat the 27 days on certain fields, or will it just do one field for 27 days, go on, and never repeat?
My understanding is that it will not repeat, but of course there's always the prospect for repeating if the mission is extended beyond its nominal mission length.
And of course I assume that any interesting targets could be followed up by ground-based telescope.
And yes, and I'll comment on that few more slides. Beyond TESS, next slide, is a European mission, Plato, Planetary Transits and Oscillations of the Stars. And it will, of course, look for planets as well, and it will also study in some detail stellar variability. And so it's a pretty ambitious mission that I think could revolutionize stellar astrophysics. Next slide. It will be launched though in 2024. We'll have 8 30-day fields, but it will have 2 3-year fields. And it will consist of a cluster of 34 telescopes. I think the pupil is about 120 millimeters for each telescope. And the cadence is about 25 seconds, although a couple telescopes will look at rapid cadence. And it'll focus on objects that are in a parent magnitude range of 4 to 16. Next slide. So it will vastly enlarge the number of known exoplanet systems, especially terrestrial planet systems, down to Earth size, and we'll be able to, through a particular technique of observing small oscillations in a star, use that information to measure mass and radius around bright stars up to the habitable zone. So Plato, next slide please, will characterize a very large number of stars, and I think in so doing will lead to a breakthrough in stellar physics, as well as the discovery of many more exoplanet systems. Going along with these photometric missions, Claude, you alluded to this, that's ground-based follow-up. Next slide, please. NASA has established the NASA NSF Exoplanet Observations and Research Program, or NN-EXPLORE, at the Kippy 3.5 meter telescope. And right now, they're building a new spectrometer for that. Next slide, please. Spectrometer for that telescope, the Extreme Precision Doppler Spectrometer. And it will have a minimum precision of 50 centimeters per second, corresponding to 1 mile per hour. And you can see the Jupiter wobble speed is about 29 miles per hour, so it'll be easily resolve Jupiter mass planets or smaller. But the design goal is 10 centimeters per second, or 0.2 of a mile per hour, which would enable us to resolve the wobbles due to Earth-sized planets. And so that's under construction right now, and that's part of the ground-based follow-up for TESS specifically. Now, next slide. Now, planets offer the opportunity to probe at a spatial resolution that we could not possibly obtain from the ground. And to the right is the Kepler spacecraft, and to the left is a panel of a planetary transit, and you can see some bumps at the bottom of the transit. And this is due to the planet transiting across spotted regions on the star. And so what happens as the planet begins to enter the spotted region, it uncovers the brighter photosphere of the star that it was covering before, and covers the dim spot. And so that's why you get a relative increase or bump in brightness. And so we can use these as probes of stellar surfaces. Next slide, please. And so I actually have a program on the NASA SOFIA Airborne Observatory to use a couple of instruments, one in the optical called HIPPO, or high precision optical spectrometer, and FlightCam, which is an infrared instrument. And by looking in both the visible at very slow bands and the infrared, next slide, or next click, I can measure the relative of brightness in different magnitudes. And the equation shows the decline on the left is called the color excess, that is the color of the spot relative to the color of the star. And that's related to the amplitude of that bump in the light curve and the fractional area coverage of the planet, which is known a priori. And so in this way we can begin to measure temperatures because the color, this color difference, is related to the temperature of the spot. And by determining the spot temperature, we can learn other parameters like the size of the spot and perhaps infer magnetic field strength and see if they differ significantly from that on the sun, or if they're the same but the spots are just bigger. Or so those are the kinds of objectives that this program is addressing. Now, the ultimate goal, next slide, in exoplanet studies is to actually image planets around other stars, and the exo-C on the left and the exo-S are sort of exoplanet imaging concepts, with the exo-C meaning referring to an internal coronagraph to block out the star's light and reveal the faint images of planets around the central star. And on the right, the exo-S is a different concept. It's an external occulter called the star shade, which would fly tens of thousands of kilometers away from the main spacecraft and be maneuvered across to a star, and it will block out the light as well, and be a very sensitive way to reveal planets around the other stars and potentially get then spectra of the planets. Now, this technique that we call the star shade, next slide please, are shown here in prototype configuration, showing that it's a petal-like structure, and the petals are designed to sort of diffract light out from what we call the inner working length angle, or that is at angles close to the star, and diffract the starlight out to other angles, so that planets that are near the star can be revealed. And so next slide shows a group from Northrop Grumman setting up a prototype of a star shade in a desert site for testing, but ultimately they decided to go to a real telescope. Next slide. And so they've begun star shade testing at the McMath Piers. So next slide, please, shows the star shade mounted near the heliopad at McMath Piers. And in the next slide, you see some initial results. On the left is Jupiter obscured just by a circular disk, and you can see some of the moon. And then on the right is Jupiter completely blocked now by the star shade.
Wow. Nice.
So you can see the moons are more visible and brighter. You don't have that glow either. So it's potentially a very promising technique. And the idea, as I mentioned in the next slide, is to eventually, once you isolate those planets with a star shade, they use a spectrograph to take spectra of these planets. And here shows comparative spectra of Venus and yellow on the top, and Earth with cirrus, and on the bottom is Earth with ocean, and then Mars, and you can see the obvious differences in the spectra, mainly due to water and oxygen. And of course, as it points out here in this slide, that testing atmospheric oxygen and water likely indicates life. Although there are some abiotic ways, especially to create oxygen, though it's not clear those abiotic waves can be sustained. So it's probably perhaps a decisive indicator of life. And next slide, please. So the initial list of missions that NASA is considering now includes, among them, the habitable exoplanet imaging mission, which would focus on exactly using a coronagraph to isolate planets and then take spectra. And next slide. Here are just some of the specifications for what we call HABEX. And it needs to achieve high contrast at 10 to minus 10. Right now from the ground, the best we can do is about 10 to minus 6. So it's a significant leap that is absolutely necessary to detect Earth-sized planets. Click again, you can see that this camera is intended to get low-resolution spectra at about 30th magnitude. And what's that's the brightness of a terrestrial-sized planet and nearby stars. But it will have to integrate for actually weeks to get enough signal noise at those magnitudes. That's interesting, a kind of interesting side effect, you might say, of that is in the next slide. It's illustrated here where it shows a simulation of a coronagraph with a planet, but when you integrate that long, you get confusion with the cosmological background. It's shown this on the deep image from the Hubble Space Telescope, showing many galaxies. But I'm sure that we'll be able to distinguish the planet from the background by various ways, such as the color. And during weeks, there may be a little bit of orbital motion that we'll see that would be visible in the cosmological background. Now, next slide. I think I'm going to skip over that because we're running out of time. And if you go to the next slide, it says stellar magnetic activity and planet atmosphere illumination. The activity of the star does have an effect on the kind of spectra you will see in exoplanets. And so an active stellar atmosphere is higher UV radiance. You can see in this slide in the upper panel that for example, the water lines are more shallow. In an inactive star, the water lines are deeper. And that's because the UV radiation from the active star will disassociate some of these molecules. An inactive star that doesn't have as much UV radiation in its magnetic regions, because there aren't as many, the water lines and oxygen lines will be stronger in absorption in spectra that we will eventually take. Next slide. And stellar activity, of course, can have tremendous impacts, potential impacts on an exoplanet atmosphere. The simulation shows a strong flare event on the sun impacting the magnetosphere of the Earth. And you can get all sorts of effects like heating the upper atmosphere and disruption of the ionosphere. Of course, aurorae are a well-known phenomenon. But around M-dwarf stars, habitable planets will have to be in close proximity, which means that they're even more susceptible to the potential effects of activity. So in the next slide, this shows a model of what might happen when a flare impacts the atmosphere of a nearby Earth-like atmosphere or planet to an M-dwarf star. And it shows the fractional change in ozone depth. When the flare occurs, you can see that the ozone declines by at least a factor of 10 due to the impact of high-energy particles into the atmosphere. And that produces nitrous oxides, which catalytically react with ozone to break it up. And if you look at the time in seconds and work it out, the ozone layer doesn't recover for about 50 years. And this is just one major flare event. Now, some people think, or most people think that if the planet has a magnetosphere, like our Earth does, then it will be protected. But in the next slide, it shows the comet Enki here, and it's about at the distance of Mercury in this movie taken with the stereo spacecraft that are observing the sun. And what you see is a wisp of the coronal mass ejection going by. and it rips the tail off. And it's not due to mechanical effects that you might intuitively think. Instead, magnetic fields in the coronal mass ejection are interacting with fields in the tail that then annihilate those fields, and it's no longer able to confine the plasma and rip it off. And it rips off the tail. And so in the next slide, you see a similar thing that happens when a coronal mass ejection hits a planet with a magnetosphere that's nearby, like we might have in an M dwarf system. And you can see that as an impact, it just blows away the magnetotail and significantly compresses the magnetosphere. And as a result, you get significant heating of the atmosphere and can lead, in fact, to atmospheric stripping in at least these models. Well, ultimately, models have to be confirmed by observation. And so in the next slide, that leads me to observe with the Kepler spacecraft. And in the upper panel shows flare energy versus rotation period. And the strongest solar flares have energies about 10 to the 32 Earth. And you can see these flares are 10 to the 34 to, I can't even read it, it looks like 10 to 36 or 10 to 38.
10 to 36 it shows.
But they're orders of magnitude above, stronger than the most energetic flares yet observed on the sun. And you can see in the lower panel is the number of such flares per year, per star, and versus rotation period. So at short rotation periods, you know, there's a higher frequency which then declines for longer periods. You can see in the upper panel, there's kind of a trend toward lowering energies with longer rotation periods, but even at long rotation periods, you get highly energetic flares. So the question then becomes, you know, can planets in the habitable zone survive these highly energetic flares? And what about our own sun? Will it someday have huge flares like this? And our very technologically sensitive society is very much vulnerable to this kind of activity.
Wow.
Mark, do you have time for any questions?
Yeah, sure.
Do we have any questions from the group here?
Yeah, on the those super flares, the 10 to the 38 ergs or whatever it was, how often do those occur in an individual star?
Well, it's somewhat dependent upon the rotation period, and the estimate is for a star rotating like our sun, namely the sun itself. The frequency about once every 5,000 years.
Oh. Okay.
So you know it's not, you know, something that's frequent, although on more rapidly rotating stars, you know, you can see some, you know, about 2% of the time, you can see a super flare occurring. So during sort of the main sequence evolution, especially during a young solar system, that could be significant, could have a significant impact. But
okay, so
you know, it's a long period in a human time frame. That's a short period in stellar evolutionary time frame.
yeah. Very interesting. So even for long period rotators like our sun, they have enough observations to see something that happens only once every 5,000 years.
Yeah, that was a calculation that I saw. So it's infrequent, but when it does happen, it could be devastating.
Oh,
Now I don't know when the last super flare was on the sun. It wasn't, you know, something that was. I mean, there was the so-called Carrington event in the 19th century, sort of during the time when telegraphs were you know, ramping up, and that shorted out a lot of telegraph systems, sent literally sparks flying. So in our society, our electronics are much more widespread and more sensitive, including our space assets.
Sure.
We've lost, very significant amounts of money in hardware, in the form of hardware in space that has been impacted by solar flares.
I have another question. Thank you for that answer. In the Kepler data where I showed the two regions of variability versus chromosphere emission strength,
Right.
there was a lower region where the sun was a member, and then there's the upper region where much more variability.
Right.
Do we know what the cause of the difference is?
Yeah, so the thought is in the more variable ones that they have higher area coverage of magnetic regions, and in particular they have a higher coverage of spot regions. That leads to higher range and photometric variability. And then when you get to sun-like stars, the spots have lower area coverage, and it's more dominated by the weaker magnetic field strength but brighter active regions. And their range of photometric variability is less. So in summary, it's kind of a competition between the area coverage of spots and bright plage-like regions. And the more active stars, the spots begin to dominate over the plage, while the less active stars like the sun, the plage, bright fascicular regions dominate over spots.
Okay.
Any other questions?
In one slide, you were talking about the two models for the dynamo, one being the interface between the radiative zone and the convective zone, and the other being a distributed model throughout the convective zone. It would seem that in dwarf stars that are fully convective, does that mean that it kind of has to be a distributed dynamo?
Yes, and so the thought is that in that case, the fields would not be in this interface region where they could be amplified and then eventually break out and float to the surface and form strong magnetic flux regions and give rise to cycles. So it's thought that the distributed dynamo and like you mentioned, those M dwarf stars that are fully convective, in those stars it's thought they would not have cycles.
Oh, I see.
We're seeing tentative evidence that they may have cycles. So either that picture of how the dynamo operates is wrong, or perhaps our understanding of those individual stars, maybe they do have some remnant radiative interior and have a shell, an interface region around that. So it's important right now to get more observations in a much larger sample of those M dwarf stars that we know for sure are fully convective and that we can monitor for a while. But those stars, as you know, are more faint, and that's why a telescope like the Large Synoptic Survey Telescope will provide valuable information for thousands of such stars. So we can examine exactly this question.
Any other questions? Well, Mark, thank you very much, and thank you for suffering through our technical difficulties here. Still an excellent talk. Thank you so much.
Thank you.
Yes, thank you.
Thank you for.
Okay, and hopefully we'll see you out here at BBSO for a meeting or something someday again.
I look forward to that.
Take care, Mark. Thank you.
Bye-bye.
Good night.
Good night.
Bye.
Good night.